Hello, students. In today's lesson, we will discuss the atmospheric and vacuum distillation towers. The primary distillation column, atmospheric tower, and vacuum tower are all distillation equipment. Under the condition of internal reflux within the distillation tower, vapor and liquid undergo multiple countercurrent contacts on the trays, performing interphase mass and heat transfer. This effectively separates the various fractions in the mixture under different temperatures and pressures, thereby obtaining products with different boiling ranges. First, let's study the primary distillation column together. The primary distillation column separates overhead crude naphtha from the top as reforming feedstock, has no side stream product draws, and the bottom liquid enters the atmospheric tower for further distillation. So when is a primary distillation column used? There are two situations. First, when the gasoline fraction content in the crude oil is close to or greater than 20%. Second, when dehydration is ineffective, water can be separated from the top of the primary distillation column. Some atmospheric and vacuum units do not have a primary distillation column but are equipped with a flush distillation tower, DED. Installing a flush distillation tower allows for the removal of light gas components and enables water in the crude oil to vaporize in the flush distillation tower. The topped crude then enters the atmospheric furnace, thus reducing the light components entering the furnace and avoiding impact on the operational load of the atmospheric tower. Let's look at the atmospheric tower next. The atmospheric tower is a complex tower. Crude oil is split via atmospheric distillation into 4 or 5 product fractions like gasoline, kerosene, light diesel, and heavy oil. According to general multi-component distillation methods, N1 distillation towers are needed to separate a feedstock into N fractions. However, the crude atmospheric distillation tower achieves this by having several side draws on the side of the tower to obtain the multiple product fractions mentioned above. It's as if N towers are stacked together, hence the name complex tower. Both the feed and products of the atmospheric tower are complex mixtures. Atmospheric distillation of crude oil yields fractions with different boiling ranges, such as light distillates like gasoline, kerosene, diesel, and atmospheric residue. These products are still complex mixtures. Product quality is controlled by various quality standards. For instance, the dry point of the gasoline distillation range must not exceed 205 degrees Celsius. 35 to 150 degrees Celsius is the naphtha or reforming feedstock range. 130 to 250 degrees Celsius is the kerosene fraction. 250 degrees Celsius to 300 degrees Celsius is the diesel fraction. 300 to 350 degrees Celsius is the heavy diesel fraction, which can be used as catalytic cracking feedstock. Greater than 350 degrees Celsius is atmospheric residue. To be refined, crude oil first moves from tank farms to the atmospheric and vacuum unit. It is then boosted by crude oil pumps, exchanges heat with hot streams, is desalted and dehydrated in the electric desalter, heated further, undergoes initial distillation in the primary distillation column, heated again in the atmospheric furnace, and finally enters the atmospheric tower for distillation. The atmospheric tower produces gasoline overhead, heavy diesel, light diesel, and kerosene from side draws, and the bottom liquid goes to the vacuum tower. Taking a 1 million tons per year atmospheric distillation unit as an example, its atmospheric tower shell weighs about 464 tons, is 42.1 meters high, 8 meters in diameter, and is the core equipment of the entire atmospheric and vacuum distillation unit. The tower shell material is generally alloy steel for units processing high sulfur crude oil. The inner wall has a stainless steel liner. The tower heads are generally elliptical or hemispherical. The bottom section is constructed with a certain height to ensure the bottom pump has sufficient net positive suction head (NPSH). Trays or packing are the medium contact surfaces inside the tower. one of the three key elements for mass transfer process. Nozzles and openings are components that connect the tower shell to other parts. They are generally made from seamless steel pipes of different diameters, welded to the tower shell with flanges. Manholes are used for entry into the tower for installation, maintenance, and inspection of internal equipment. They are typically circular or oval openings 450 to 500 millimeters in diameter. Vapor distributors are usually installed where vapor enters the tower, aiming to distribute the vapor evenly. External insulation is typically built with insulating bricks, fixed with screws, and covered with thin steel or aluminum cladding. The insulation layer provides thermal insulation. Finally, let's look at the vacuum tower. The atmospheric tower bottom liquid is heated in the vacuum furnace and then enters the vacuum distillation column. The tower top does not produce a product. Only non-condensable gases and steam are separated. Condensed and the non-condensables are extracted to maintain the vacuum state. Side streams draw off lubricating oil or cracking feedstock. The bottom is vacuum residue, which is also stripped of light components using superheated steam before leaving the tower. High boiling point fractions above 350 degrees Celsius in crude oil are feedstocks for lubricating oil, catalytic cracking, and hydrocracking. However, because decomposition reactions occur at high temperatures, these fractions cannot be obtained under atmospheric tower operating conditions. They can only be obtained through vacuum distillation under vacuum and lower temperatures. With modern technology, fractions boiling up to about 550 degrees Celsius can be distilled from atmospheric residue via vacuum distillation. The core equipment for vacuum distillation is the vacuum fractionator and its vacuum system. Depending on the production target, vacuum towers can be classified into two types: lube oil type and fuel oil type. Generally, regardless of the type, a vacuum tower needs the highest possible distillate yield. This is because the distillate oil has lower carbon residue and very low heavy metal content, making it more suitable for lubricant production and as cracking feedstock. The vacuum residue from the bottom can be used as fuel oil, coker feedstock, residue hydrotreating feedstock, or processed to produce high-viscosity lubricants and various asphalts. Below is a look at the product structure of the primary distillation column, atmospheric tower, and vacuum tower. The overhead product of the crude tower is crude naphtha. The overhead product of the atmospheric tower is gasoline. Vacuum tower overhead, no distillate product. Primary distillation column, side streams, none. Atmospheric tower side streams, 3 draws, becoming progressively heavier from top to bottom. Vacuum tower side streams, waxy oil, gas oil, fractions. Atmospheric tower bottom, atmospheric residue, catalytic cracking feedstock. Vacuum tower bottom, vacuum residue, coker feedstock. To ensure the quality of side stream products, both the atmospheric and vacuum towers are equipped with side stream strippers. That concludes our discussion on the primary distillation column, atmospheric tower, and vacuum tower for this lesson. This lesson is now complete. Goodbye, students.